Every massive computational journey begins with a single foundational problem. For OpenML, that problem wasn't a sprawling data lake or a chaotic enterprise pipeline. It was a stack of Latin vocabulary cards. We wanted to map human knowledge from its most rigorous grammatical roots, texts like Newton's Principia and classical Loeb literature, into a system where logic is completely unadulterated. We didn't want a black box AI model guessing at the meaning of our data, hallucinating connections, or muddying the rules. We wanted absolute mathematical sovereignty over our knowledge base. And that quest for absolute control led us directly to the intersection of physics and linguistics, quantum natural language processing. Our first major milestone in this new universe was building a quantum part-of-speech tagger for Latin. It takes the abstract theory of quantum natural language processing and applies it to one of the most fundamental tasks in computational linguistics, and one that is uniquely valuable for a language learner trying to decode complex syntax. In classical machine learning, a part-of-speech tagger typically looks at a word and its surrounding neighbors, processing them through a neural network to output a flat probability distribution, something like 90% noun, 10% verb. But to do this on a quantum architecture, we map our Latin vocabulary to parameterized quantum circuits. Instead of updating flat weights in a matrix, our PyTorch optimizer will physically adjust the rotation angles, theta, of the quantum gates. We will train the model to rotate the qubits into specific mathematical states, eigenstates, that correspond to noun, verb, or adjective. The quantum part-of-speech training architecture we engineered is a complete runnable PyTorch script using Lambeck to train a quantum classifier. We define a small subset of words, build their quantum circuits using the IQP, or instantaneous quantum polynomial, ansatz, and use a standard cross-entropy loss function to force the quantum gates to learn the correct grammatical categories. During gradient descent, the loss function calculates exactly how much we need to physically rotate the phase of the qubits so that the measurement aligns perfectly with the correct grammatical category. At epoch 0, a word like viz exists in a pure state of language superposition, an equal probability of being anything. But as the optimizer iterates, it tunes those specific phase angles. By the final epoch, the wave function collapses cleanly into the noun measurement basis. From a single Latin phrase to the infinite dimensionality of human thought, this is the blueprint for our sovereign architecture. This is OpenML,